11.2, inference for relationships. Last class we looked at 11.1, the chi-squared goodness of fit, and that was if you have one sample group and you're comparing to one distribution that you believe is true about the population, meaning that you have proportions that you feel that population fits, and you're trying to see, does your sample fit what you believe is true about that population? Now, in chi-squared tests, which we're doing today in 11.2, you have two sample groups. Maybe you have two populations, or maybe you have one population, but you have two groups out of that population. So now we're trying to see an overall test. Is there good evidence of a difference in the parameters that we're trying to compare? Maybe from population to population, maybe from characteristic to characteristic. Categorical data and requiring the chi-squared test, which is a test for categorical data. And then if we find that there is a difference, then we do want to have a follow-up analysis where we decide what thing was the largest contributor to this evidence that we find of a difference. So there are two types of chi-squared tests. They actually are performed in the exact same manner, and that's why your calculator only has the one chi-squared test button. Okay, not to be confused with chi-squared goodness of fit, but chi-squared tests, there's homogeneity and there's association independence. Those tests, we will find our expected counts. Generally speaking, we've got a two-way table. So in our two-way table, we are going to find our expected counts by doing the row total times the column total and divided by the table total. And really what you're basically doing is finding what percentage you expect in that area and then multiplying by the either column or total or the column total to like see how many you would expect to be there. And I'll explain that on the other page. And then you can see that your chi-squared contributions are all calculated the exact same way with your observed minus your expected, that quantity squared over the expected. And then you'd add all those chi-squared contributions up and see if there's enough evidence to reject the null hypothesis. What degrees of freedom will we do to get that p-value? We will take the number of rows and subtract 1, and we will take the number of columns and subtract 1 and find the product of those two numbers. So your rows minus 1 and your columns minus 1, and that will help us find the degrees of freedom that we will then use to find the area or p-value to the right, because remember, chi-squared curves are not normal. You should never use the word normal when referring to chi-squared. So chi-squared is right skewed and absolutely not normal. If you write that down, that would be a very big no-no if you said that that was normal. Okay, so first, why don't we try to figure out how to identify which type of test it is. If you're in the chi-squared, if you're doing a chi-squared on the AP test and you are not absolutely sure whether you had homogeneity or association independence, then just call it a chi-squared test, because you would rather say less and be correct than say more and be wrong. So what is the difference between a chi-squared homogeneity and a chi-squared association independence? They're asking kind of different things. The homogeneity test is checking your categorical variable, but it's checking it for several populations or treatments. In a chi-squared association independence test, then you basically have one population of interest, right? One population of interest, but you're checking two variables out of that population of interest, and you're trying to see if there's a relationship between the variables. So one is looking at, for this variable, is there a relationship between group 1 and group 2? That's homogeneity. And in number 2, it's I've got a group. Within that group, is there a relationship between what I'm measuring for these guys and what I'm measuring for these guys in that same group? The two things that I'm measuring for these people in the same group. So that's the difference. And so when we word their null and their alternative hypotheses slightly differently, and sometimes deciding if you're looking for, if we look at the way those are worded down here, and you can read through the rest of that page. If you're looking for a chi-squared test for homogeneity, then you're looking for there is no difference in the distribution of a categorical variable like heart attack rates for several populations or treatments. And then number 2 would be there is a difference in the categorical variable for several populations or treatments. So an example might be if I look at men and I look at women and I keep them separately, and I take a sample of men, take a sample of women, is there no difference in the heart attack rates for men versus women? The alternative, there is a difference in the heart attack rates. Notice how I'm saying context. Heart attack rates for men versus women. Okay, then now this second one, that was the first one. So I had men and I had women, and I took a little bit of men, I took a little bit of women, and measured their heart attack rates, and I compared them. Now, chi-squared test for association independence. Now in this situation, I'm going to use the same example with the heart attack and the men and the women. But what I'm going to do is I'm going to conduct my research slightly differently, and it's going to change the type of test that I have. So if I'm, instead of finding men and then finding women and then sampling them for their heart attack rates, let's say instead I just go and get people. I go and get a group of people, one population, they are people, and then I say when I go out there and I measure about them, I measure their heart attack rates and I measure their gender. Then what I've done is I have two things I'm measuring about my one population, and I am looking, there is an association between gender and heart attacks for people. That's how I would reword that. There was no association. And then the alternative is there is an association between gender and heart attack rates in people, keeping it in context. Association independence, you can also word it as using the word independent, meaning the heart attack rates and gender, I'm replacing two categorical variables with the context, are independent for people. Heart attack rates and gender are not independent for people. So you can see the difference of how it was conducted will change what kind of test you're doing, but the test itself will be conducted in exactly the same way because there's that real relationship as you saw there. So on this next page, we're going to try to see if we can tell which kind of test we're doing. Is this a homogeneity test or is it an association independent test? So think about how you have to have things separate and then you gather data and then you analyze. Or did you have a big group, you gathered your data, then you separated, and then you analyze. So there's that order. So think, for homogeneity, you're going to be wanting to be separate. Then you're going to gather your data. and then you're going to analyze. In a association independence, you're going to have a big group. Then you're going to gather your data. The data helps you separate them. Then you're going to separate. And then you're going to analyze. Analyze. Okay, so let's read this first one. Market researchers suspect that the background music may affect the mood and buying behavior of customers. One study in a supermarket compared 3 randomly assigned treatments, no music, French accordion music, and Italian string music. Under each condition, the researchers then recorded the numbers of bottles of French, Italian, and other wine purchased. So it looks like before they started gathering data, they first had it separate. Separate. Because they had the different treatments. Then they gathered their data. And then they analyzed. That is a test of homogeneity. Feel free to pause the video, attempt to do the rest of the problems, then fast through and see if you get the same answers I do. Are men and women equally likely to suffer lingering fear from watching scary movies? They took a sample of 117 students to write a narrative about their exposure to scary movies before age of 13. More than 1/4 of the students said that some of the fright symptoms are still present when they are awake. The results were broken down by gender. So it looks to me like they had a big group. Then they gathered the data. And then after gathering the data, they broke them down by gender. And then they analyzed. So that would be a test of association. If you want to use an association between lingering fear and gender, or is lingering fear and gender independent? So either of those would work. Okay, read through, pause the video, read through the next examples, and decide what you think, if you think it's homogeneity or association independence. Separate random samples, cell phone only, landline, separate, then gather your data, homogeneity. Cocaine addicts, separating the people into their treatments. Prior to gathering data, you've separated, even though you started with one big group, you have separated them into their treatments first, then gathered your data, homogeneity. Is there a difference between the drug's effectiveness? Last one. Big group of people. So but now we have to see did they separate them before gathering the data or after gathering the data? They're going to record the information about their sudden anger. They're going to record their information about coronary disease. And then after that, analyze then separate the people by the characteristics and analyze that. That's an association independence. So here's the results of a study. They suspect that the background music affects the mood in buying, how much wine they're going to buy, which type of wine they were going to buy. And so you would want to do your conditions for analysis if you're going to be doing a chi-squared test. And before we do that, let's just look here. This is what we would have done in chapter 1. We would have taken our two-way table of categorical data, and we would have made bar graphs, and we would have compared these bar graphs. We would have compared the levels, and I would see that this Italian wine level seems to have a marked change from graph to graph. Is this change significant? It looks substantial for sure, but is it significant? And then when I look at like the other wine, those are very similar levels if I was doing a comparison. But now I'm going to look and see, is the Italian wines different enough to be, according to the chi-squared, and when we look at all these contributions together, is there enough to say that something's different? So to do our conditions for a chi-squared test, let's do that first. We need to know if it was done randomly, and we are not going to overly talk about randomness unless we see a clear violation of randomness, like they only went and did this in stores in Little Italy. Then maybe that would be a problem because it would have bias. So with the randomness, you're really looking for if there was bias, but this was given that they did a random situation. Independent. And I would say, because I would just go with my 10% check just to keep it easy. I would say that there are more than 2,430 customers, most likely. So I feel like that's it. And then for, that was check 1, check 2, but then check 3, is it large enough? And remember, that kind of comes about by actually looking at the categories. Will these categories, these expected counts, be large enough to over 5? And we'll have to do some. Let's do some expected counts. I do know that they are all expected counts will be are over. I know that they will be, so I'm going to just write that. And that will meet that condition, the large enough a condition, which is the new condition that we have. We talked about how this is going to be a chi-squared test for homogeneity on the other page. Therefore, let's write our null and our alternative hypothesis, and we're going to learn how to use the calculator for this. But let's write our null and alternative. Given it's a test for homogeneity, then I would say there is no difference in wine type for the various music. Purchased. And that I am going to compare to my alternative, and the alternative is there is a difference. In wine type, and looking at those conditional distributions from the bar graphs, I feel like there is for Italian. Okay, so I've written the alternative and I've written the null. So now I'm going to go over and find some expected counts. I know that I've already said that the condition, the large enough condition was checked, but really I would have done the expected counts, and I will show you how on the calculator we can do them very quickly. But let's just look at, for example, like the French with no music. What would the expected count be for that? You have, let's see, for French wine, you expect 99 out of 243. You expect 99 out of 243 to be French. You expect 31 out of 243 to be Italian. You expect 113 out of 243 to be other. Now, if I know what this number 99 out of 243 is as a percentage, I then multiply it by the 84 to see what percentage of the 84 do I expect to show up in French no music. So really that formula of my, I put the column total first, but the row total and the column total multiplied by each other, divided by the total, it's really looking at what percentage you thought would be in that category and then multiplying by either the row total or the column total, whichever one you didn't use, to see how many you expect to be in that area. We expect 34.22. And then if we have our Italian no music, we expect 84 times 31 over 243. We expect, let me punch that in. 84 times 31 divided by 243, we expect 10.716 to be in that category. So that's just a couple expected counts. I'm going to show you how on the calculator we can get all these numbers extremely quickly using matrices. But that's just illustrating the calculation. Now, if I wanted to find my chi-squared contribution for my French no music, I would take my observed amount of 30. I would subtract my expected number of 34.22, and I square that, and I divide by my expected, and I get 0.5204. So it's fairly close to what was expected, the observed. This is Italian no music, my chi-squared, and I see that as 11 minus 10.716, and then divide by 10.716. Oh, I forgot to square it. And I get 0.00731. And so those are just some of the chi-squareds that Italian no music is very little contribution. What would my degrees of freedom be for this problem? My degrees of freedom is going to be my row minus 1 times my columns minus 1. And so my degrees of freedom will be, I had 3 rows. not to include the total row. So 3 minus 1, it would be my rows, and my columns, again, not to include the total row. And so my degrees of freedom is 2 times 2, which is 4. So I have 4 degrees of freedom for this problem. Now what's really nice is that if I'm using the calculator for a chi-squared test, it's incredibly easy. We can immediately get our chi-squared expected counts right away. It's a little bit more tricky to get the contributions for the individual items. I usually just enter it back into a list in the calculator, and I'll show you that. But let's just write down that we're going to go to our calculator, and when we go to the calculator, we're going to be going to matrix. So you could hit that matrix button. We are going to go into the matrix, and we are going to edit our matrix, and we are going to select probably matrix A. I would select matrix A, and matrix A will be a 3 by 3 matrix. So we will have to tell it this first number being the rows and this second number being the columns. We will enter our data. Then we will use calc tests, and we will do a chi-squared test, and the calculator will generate matrix B, and that will be equal to our expected counts. So we're going to see how that goes, and it will also tell us our p-value and everything else that goes with this. So let's see, I don't think I've entered that matrix in yet, so we may have to enter it. Second matrix. No, I didn't enter it in yet. So I go over to edit, and I have to put in the 3 by 3, and see how it automatically makes it to the right size. Now I'm entering my observed counts into my matrix. And now I'm just going to double check that I've entered all those numbers correctly. That is my matrix. Now, it's very important to make sure you've hit enter on that last one, because sometimes you think you've entered that, but you haven't actually entered it. You could even go to a different spot just so that you know that that last number has really been entered. So I'm going to quit the matrix. That's one trick. I'm going to stat, going over to tests, going down to my chi-squared test, not my chi-squared goodness of fit, which was for one population fitting proportions, a distribution of proportions. I'm doing not the goodness of fit, I'm doing one up from that. I'm doing the chi-squared test. And it says, where do you have your observed values? I have them in A. Where would you like me to put the expected values? B. And let's calculate it and go. And it actually does generate the degrees of freedom for you, but it tells me that the sum of the chi-squareds was an 18.279. My p-value is 0.001088, so that's rejecting at the 0.05 level. I'm going to reject my null hypothesis, and I'm going to conclude that the alternative, that there's evidence to conclude the alternative is true. Because I'm rejecting the null hypothesis, I need to know which category was resulting in the rejection. So I'm going to go back to, and this I did enter the numbers in already, into my list, you can see that I have entered 30, 11, 43. That's the none list. 39, 1, 35. That's the French. These are my observed values. And then if I go down, oops, I'm in the wrong column here. If I go down, you can see that I've entered the Italian of 30, 19, 35. And then I have already entered these numbers, which I got from matrix B. Let's see matrix B. Here is matrix B. Previously, it was not a 3 by 3. They have created that matrix. I can either hit enter on the names. Whoops, that don't want to do that. Clear, escape, second quit, clear. Hopefully I didn't mess that up. I can either hit just enter on matrix B and it'll, boom, show me matrix B. That's a little awkward though, isn't it? Seeing those values is awkward that way. So I'm going to go back to my matrix and instead I'm going to go to the edit feature and make sure you're looking at matrix B. So you can see that's where I got my expected counts would be from matrix B right there. I actually rounded a couple of those numbers when I input them. So here are, those are the expected counts back to my list here of they've been entered in. So I need to see which contributions are, because I'm rejecting, I have to do this step here of figuring out which wine is making me reject. So the largest contributor by far is the one in the observed, but I expected a 9.57. So that would be the French wine. Let's see, that's the Italian wine, but with French music. I'm seeing a huge thing. This is that's almost 0 right there. And there's another one. I also see a huge contribution on the 10.72. So that would be Italian wine again, but this time with Italian music. So Italian wine purchases appear to be very affected. And the next page shows what Minitab output would look like for this exact same situation. And so this would happen frequently. They're going to give you the Minitab output for the chi-squared analysis. And so the way this is going to be set up in the Minitab output is, and this first one was our, this was French wine here when you purchase a French wine, and then this is the Italian, and this is going to be the other. So those are your purchases, and then this was the music that's being played, your observed, your expected, and your chi-squared contribution. So if you look on here, we actually see these chi-squared contributions for each of the types of wine. The one I'm circling now, the Italian wine purchases with no music, that one has a slight rounding difference just because they used different numbers. I mean, they used a more rounded number. See, effectively 0 on that one that I had times 10 to the negative 4. And so those are my chi-squareds. Here's my sum of the chi-squareds. Here's my degrees of freedom. Here's my p-value. They are going to 3 sigs. That's very, very low. And so we would say to conclude this situation, we would say that we have a p-value of chi-squared going above a 18.279 will be 0.001. Since the p-value of 0.001 is less than alpha equal 0.05, we reject the null hypothesis and there is significant evidence that there is a difference in wine purchase for various types of music. And because I had a reject of the null hypothesis, then I need to look at the largest contributor. So the largest contributor was Italian wine purchases when French music, and I'm going to put the number because that's important. Chi-squared for French music, Italian wine, the chi-squared was a 7.672. French music, when French music or Italian music, I put the chi-squared in there. I want numbers to give me an idea of what we're really talking about was being played. So that was a chi-squared test for homogeneity, looking for a difference when you did that. And if you wanted to use the word respectively in your writing, if you wanted to say the largest contributors was for Italian wine, for French music and Italian music with 7.672 and 6.404 respectively, then you would know that the French music went with the 7 and the Italian music went with the 6. Okay, so we'll do another example and we will use our calculator for these examples because that's what I would highly recommend doing. I would have gotten the same result by adding my L3 and then doing the p-value, but it just seems like with this calculator, it's so much faster and easier to use the matrices. So let's do that. So, okay, random digit dialing. Let's find out what kind of test we're going to be doing. It's definitely a chi-squared, but which kind? So we've got random digit dialing surveys, and they're used to exclude cell phone numbers if the opinions of people who have only cell phones differ from those of people who have landline service. The poll results may not represent the entire population in that case. The Pew Research Center interviewed separate random samples of cell phone only and landline telephone users who were less than 30 years old. Here's what the Pew survey found about these people and their party affiliations. So it sounds like we had a group, we then had them, they were separated, we gathered the data, and then we analyzed. So this is another situation of homogeneity. And we want to know, is it random? and it was given that it was an SRS. Is it independent? Since we have finite people, I think in the store we probably could have made the case that that it wasn't finite, but here we definitely have a finite number of people out there in the world. I would say that 200 though is less than or equal to 10% of n. You know, if more than 2,000 phone owners, I'd say that's probably reasonable. And then are large enough a condition? And it probably would be helpful to know what our chi-squared expected counts are going to be. I think in order to, I'm going to put my observed, I'm going to make a list just so I can keep this kind of organized, and my expecteds right here in case I need to get the chi-squared contributions. I'm going to stay organized and list them. Don't list the totals. And I'm going to be able to get those expected counts from my calculator. And when I get those expected counts, I'll be able to check this. And if my conditions are met, if my conditions for inference are met, what will I do? A chi-squared test for homogeneity. And at some point, I do need to write my null and my alternative hypothesis, but let's go and see what the results would be and run our test. And we'll write down all the information from our calculator. So just to review, into our calculator, into the matrix, where I will edit my matrix A. No need to clear matrix B because matrix B will be overwritten. I am a 3 by 2 now, not 3 by 3. Don't enter the totals. Make sure you've hit enter on that last one. I find sometimes just to move your cursor to see if you actually have the 30 there. I do. I am going to quit and go into stat tests. This will help people on the AP Bio test. The AP Bio test here. And you know, you might have this. When my daughter took this test, there was a chi-squared on the AP that year. Okay, it's going to overwrite matrix B. Let's calculate. Let's write that stuff down. I'm encouraged by the fact that the p-value is greater than 0.05. I would not bother entering the data into my L1 and L2 because there will be no follow-up analysis needed. So I'm actually going to write down those numbers on this page, but I do need to, in order to verify that condition, and in order to get my points, I do need to show, whoops, I prefer to go this, not at, oh, actually it's kind of nicely rounded there. So I do need to write down those numbers, which is my matrix B. So those numbers I will have to write down on my paper, and I would write them down. So you might have written them down next to the original data, but I prefer to write it down in an organized manner. So let's write it down. Writing those numbers from the matrix. If there had been follow-up analysis, I would have put these in L1 and L2. I'm not going to bother. This is no follow-up analysis required. Okay, so that's good to know. I do need to write so let's see, all counts, expected counts, all expected counts greater than 5. That's good. If they had not been, I would have had to combine some categories, but they were. So let's write our null and alternative hypotheses. I am wondering, because it's a homogeneity, there is no difference in the political party leaning, I guess, or choice, based on phone service. That'd be important to know if there was, because that would be a source of potential bias in any kind of a survey. And HA, there is a difference. In political party leading based on phone service. Now I'm going to write the information that I got from my calculator. I got from the calculator, I got that the chi-squared sum, the chi-squared was 3.2199. So that was the sum of all the chi-squareds. If you want to put the sum sign, you can. I saw that my degrees of freedom, and just to review why, it would have been 3 minus 1 and 2 minus 1, but the calculator will tell me my degrees of freedom, unlike goodness of fit where I have to do it. And then my p-value of a chi-squared being above a 3.2199 was basically, well, let's see, 0.19989, so we could call that 0.200 if I want to use 3 sigs, or just call it 0.2. And since the p-value of 0.200 is greater than alpha equals 0.05, we fail to reject the null hypothesis. And there is not, don't say no, say not, because there's some evidence, but not enough, not significant evidence that there is a difference in political party leaning based on phone service. And no follow-up is needed for that because we failed to reject. So on to the next page, which I've moved to be, this page is about, we've got this big group of people, and then we gathered data about this big group of people, and then when we saw their results, we then separated them into their groups, And so this is going to be an association independence test. Chi-squared test. So chi-squared test for association independence. So we would go through our conditions. In the interest of time, the conditions, you would look at your randomness. You would look at your independence. I feel like we know what to do in this situation. We would look at our large enough. So that one being the main one in this situation, let's put this data into our calculator, have our calculator generate the expected counts, and we will be testing our hypothesis of we can either say that there is no association between the anger and the CH coronary heart disease. There's no association. That could be our null, or we could say that they're independent from each other. Whichever wording you prefer, association or independence. But I'll just go with association. Okay, so there is no association between coronary heart disease and anger. I wonder if there is. And then our alternative would be there is an association, meaning that it's not independent between coronary heart disease and anger. So we're going to run our test. I'm going to write my, I would like to write my observed just to keep myself organized. I'm going to write my expecteds, and I'm just to keep myself organized. I'm going to get these values from the table that's going to be generated by my calculator. And there were a lot more people with no heart disease, but we're going to see, whoops, I can just write like that. We're going to see if there's some kind of relationship for this. So we're going to put this stuff in the calculator. We're going to run the situation. This is a little bit backwards. We don't really know if our conditions are met yet, but we're going to see if they're met. Going to edit. This time I have 2 rows. Whoops, 2 rows. And then I have 3 columns. So 53. If you enter those in the wrong order, you'll know it right away because it won't match what you're trying to enter. So just try it, and if it doesn't match, change it. Make sure you hit enter after that last number, and I did. So now stat test. I wonder if I had to exit before I do that. So I forgot to hit exit. I might be making a problem here. We'll see. Oh, okay, that worked. And then I'm going to calculate it. It's going to overwrite matrix B. And there you have it. So that is, and don't be fooled by that 3.2. It's 3.2 times 10 to the negative 4. That's incredibly low. There seems to be a relationship between your anger level and coronary heart disease. And because we rejected, we actually would need to come up with the contributions for this this matrix. So we actually would need to do that. So Let's go into our matrix and see what the matrix B looks like. I'm going to use edit this time. Go to matrix B, and there are my values, which I am then going to write down on my notes. And so let's write these numbers down. And my suspicion, when in just looking at these numbers, my suspicion is that these people here are going to be my biggest contributors just because of that big difference. But I would need to punch that in and find out who the largest contributors are. So I would need to know what my contributors are. Let me write down the other information. The sum of the chi-squareds was a 16.0767. I had degrees of freedom of, let's see here, 1 minus 2, or 1 times 2. So I had degrees of freedom of 2, and I had a p-value of, let's see, 3.228. That's what I've written down. Was that what that? Times 10 to the negative 4. And so we are going to reject the null hypothesis. And of course you would say, because that number, which is so incredibly close to 0, is less than alpha equal 0.05, we are going to reject that null hypothesis, and we have significant evidence that there is an association. There is, I'm just put that in parentheses. There is significant evidence of an association between coronary heart disease and anger. The largest contributor, this is important because that will inform me why is this whole door was, and then I'm going to have to put it into the calculator to see who was the largest contributor, but I imagine that it's going to be that 27. And let me just quit this, and just to say, like, that particular contributor, if I clear this, 20, oops, I need parentheses. Just want to look at that one contributor for a second here. 27 minus 14. So you really only expected to have 14.193. Remember that those decimals are important. And then divided by the 14.193. And you can see that that contributor was really almost entire deviation. It's the 16, the sum of the chi-squareds was 16.1 roughly, and 11.6 of it came from the people who have high anger. So anger really does seem to be associated with coronary heart disease. So I'm going to write that number down, 11.55. Wait, what was that? Was that 11 point? I'll go 11.6. Let's call that. So the largest contributor was the high anger group, high anger with coronary heart disease group with chi-squared of 11.6. And that was the biggest group. No units on chi-squared. That was the biggest group. Okay, and then the last page is another test for homogeneity. It's looking at cocaine addicts and looking at different treatments for cocaine and wondering if I separate these people into these treatment groups, then I gather data on them from their separate groups, and then I compare their cocaine relapses for the groups. That would be a homogeneity test. And so I'll just quickly do that last one with a calculator. And just to review that one more time, but I think it's kind of repetitive. You've seen this, but if I go to my calculator, and of course I need to know if that large enough condition is being met. Very important to have my conditions. And so I am doing a 3 by 2, and I get 10, 14. Seems a little repetitive here. You've seen these. And then I'm just going to check that I got that in there. Yep. I'm going to quit. Stat. Tests. To the chi-squared test, not the goodness of fit. I have my data in L1. It will overwrite my L2. And I can write down that I had a chi-squared of 10.5. I had a p-value of 0.00524, degrees of freedom of 2. So 10.5, 524. Oops. Probability that my chi-squared is greater than 10. 4. This is going to result in a rejection of the null, which of course would be worded in the homogeneity wording of that. And because you're looking at, is there a difference in cocaine relapse for different treatments? My degrees of freedom would be 2. Let's check our expected counts. Whoopsie, expected counts. And let's look at that. And if you want to write it in matrix notation, you certainly can. Matrices have square brackets around them, unlike a determinant, which would have straight lines. But let's look and see what our matrix said. It said, and then you can see that it's 16, 16, 16, 8, 8, 8. So we'll put that on our paper. And so if you wanted to write your matrices in matrix notation, that would certainly be mathematically appropriate. And they are all over 5. So large enough. And so that's why we were able to do a chi-squared test for homogeneity as our inference.